Hi, this is a presentation of select slides from my PhD thesis defense, which are a part of our CVPR 2025 tutorial on evaluating large multimodal models. Unfortunately, I won't be able to present my slides in person, but I figured that some of you may be interested in watching a presentation of them, so I will be uploading this run-through of my slides to YouTube. The fundamental question that evaluation research seeks to answer is this: how can we really know what generative models are capable of? There are three prevailing approaches to answering this question: core capability benchmarking, subjective analysis, and deployment time testing. In my work, I mainly address the first two because those are the things that academics are equipped to approach. The core capability benchmarking paradigm entails taking some model under test and then subjecting it to a bunch of different question exemplars. Then the model is asked to answer each of them, and its overall success rate at answering each of these questions is given as the overall score for its performance. We don't really care that much how well a model can perform simple table reading tasks or answer basic trivia. Really, what we care about when we do this core capability benchmarking is determining whether a model is relevant and appropriate to deploy in the real world. Suppose we want to build some AI-based travel agent. Under the core capability benchmarking paradigm, what we do is first look at what abstract human knowledge and human intelligence capacities get employed by a travel agent in their work. For example, the ability to know what the policies are, being able to read through timetables and examples of current flight availability and stuff, ability to do some basic math and having common sense reasoning. Then we look at some model that we want to slot in as our travel agent assistant and then say, okay, this model has sufficiently high scores on reasoning and understanding such that it is safe to deploy inside of the agent. But does this actually work? Well, in the case of travel agents, we have a real-world example where we found that they're insufficient. So Air Canada deployed a chatbot, presumably based on GPT-4 or something, which was one of the state-of-the-art commercial models at the time, that was found to be nearly perfect on measurable reasoning benchmarks like MMLU. But when a customer actually went to this chatbot and asked for a bereavement discount that was off policy, the model promised it to them, even though it's actually not a part of the policy. And that customer was actually able to sue the airline and force them to pay that discount. And this was a precedent-setting, not only an embarrassment for the company, but a big problem for companies like OpenAI, because it's basically establishing that there's liability if you deploy a model that has some unexpected failure mode like this. Okay, so that's core capability benchmarking and an illustration of its issues. Now let's talk about subjective analysis. So one example of a task where subjective analysis is predominantly used is demographic biases in generative models. So here we can ask a text-image model, give me a picture of a firefighter, and then we can observe, okay, these firefighters are all white male, and you don't have to be a white man to be a firefighter. So one proposed solution to fix this, which follows very straightforwardly from this basic observation, is that maybe we can just slot in demographic descriptors such as black, female, white, male, Asian, etc., and just randomly sample those at generation time to get an output. And if you do that, that is going to provide a more demographically diverse set of generated firefighters. But is that going to be safe to just set up your system to do that whenever a picture of a human is requested? Well, we have a real-world example of that too, where if you ask for a 1943 German soldier, you don't necessarily want to slot in these different demographic traits. And this actually happened with Google Gemini's image generation service, and it was pretty embarrassing for them because this sort of patch that followed from a simplistic subjective analysis was not robust to all the corner cases of things that could be requested. So Both core capability benchmarking and subjective analysis are failing to capture how the capabilities of the models will actually interface with the real world. And the core capability benchmarks are just modeling really simplistic things, and they aren't ecologically valid. In other words, they don't represent contextualized real-world behavior. And then the subjective analyses, while they can be more ecologically valid and they can be more sophisticated than simple benchmarks, they're not going to scale to predict complex user interactions. In other words, we're bad at evaluation. The two important questions that we need to answer for evaluation to get out of this pickle are, first, how can we know if an evaluation matters? And second, how do we measure what matters? I will be addressing these two questions by presenting to you two research projects, one on long context vision language understanding, and the other on faithfulness evaluations in text-image models. First, I'll talk about our EMNLP 2024 work, Losing Visual Needles in Image Haystacks. So what is long context understanding? Long context understanding refers to the capacity for a model to input sequences of longer context lengths. The context length capabilities of models has been going up a lot over time, and it's going to be a useful solution to some of the problems that we discussed before. For example, if the entire Air Canada regulation policies could be stored in memory of the model each time it's generating an output, perhaps it would be less prone to hallucinations. However, long context understanding needs to actually be tested. We can't just assume it's going to work as these context windows get larger. The reason why is because the attention mechanism scales quadratically with the length of the sequence input, and consequently, it's pretty much impossible to train a million token context window using dense attention the way that we train smaller transformer models. So we usually adapt these long context LMs using different kinds of engineering hacks and stuff, and we need to actually test that they work. And the problem is, as we demonstrated in this work, our tests for long context understanding in vision language models are not valid. So how do people test for long context understanding vision language models? Well, one big way is a needle in a haystack test. And for a vision language model, basically this entails taking some long sequence of frames, like a movie, and then hiding a needle phrase somewhere in one of the frames. Then we ask the model, okay, what is the keyword? And the model has to search over the entire video, find the frame where it's present, and then answer with that. They hide this needle phrase at each position in the sequence. And then by checking how accurately or checking the binary question of does it get accurately retrieved at each position, we're able to produce a retrieval accuracy graph. Here's what it looks like. Basically, it's just a bunch of green squares, where on the y-axis we have the depth, or that percent I was showing before, the position of the needle throughout the video's length. And then on the x-axis, we have the overall length of the video here in minutes. So by checking at each of these different positions, we're able to fill in with a green square when the needle is retrieved 100% of the time accurately. These sorts of graphs have been used in order to demonstrate the relative superiority, for example, of Gemini 1.5 over GPT-4v, where Google basically said, look, we can feed in a video of up to an hour long into Gemini, and it can perfectly retrieve the needle phrase at each position. Therefore, the model can actually understand those long sequences and usefully manipulate them. So the thing is once again, we don't really care how well a model can just retrieve some known hidden key phrase. We care about how well the model can answer complex contextualized questions. So in this case, suppose when we fed in Star Wars, instead of burning in a key phrase into some frame, we feed the movie into the model and then ask it some contextualized question, like why does a character get wet hair? To answer this question, not only does the model need to find the position in the sequence based on common sense that actually relates to the query, it also needs to reason about the local context. It needs to recognize that Luke Skywalker's hair is wet in this frame, and then attend over the prior frames to recognize that the monster, it is in fact a Dianoga for all of you Star Wars lore enjoyers, pulled him under the water, and that's the reason why he got wet. We dub this capability extractive reasoning, or the ability for the model to attend over the entire sequence and answer from relevant information while ignoring distractors. Now, the implicit claim that's being made under the surface in these needle in a haystack tests is that demonstration of the first capability, the ability for the model to just pull out that key phrase from the entire length, implies that the model is capable of this more complex, more contextualized, and more useful extractive reasoning capacity. But does this assumption actually hold? In this work, we actually set out to answer that question with a system that we call LocoVQA. What we do is we take existing examples from existing visual question answering tasks and then hide them in a sequence of unrelated images. This effectively simulates a really stupid and easy movie where none of the scenes are relevant to the query except for one. So in principle, this should be a pretty easy follow-on task on the simple needle in a haystack keyword extraction. We have two different ways that we allow the model to ingest these sequences of examples. The first is this composed setting, which is for models that we want to test that don't actually have the ability to ingest an interleaved sequence of multiple images. For these sorts of models, the canonical approach to providing a multi-image input is simply to concatenate all the images into a grid. So we go ahead and do that. The other class of models that we evaluate are ones that can take in an interleaved sequence. And in this case, we separately tokenize each image and feed them in order as expected. This then allows us to produce these plots of short context extractive reasoning performance. Here, just like in these retrieval accuracy graphs, on the x-axis, we have the total length of the video, in quotation marks here, that's being fed in. And then on the y-axis, we have accuracy as a percent, which you can think of as just being the y-axis, the vertical columns on the video haystack grid figure, compressed into a single number, just by taking the success rate over all the different positions. Now, the expectation is, because Gemini has demonstrated that it has perfect recovery performance at these different needles, at these different haystack sizes, we should expect that whatever performance it gets in the single image condition should be maintained as the context length increases. However, testing several different frontier and open VLMs in both the interleaved and composed settings, we find that across these diverse data sets, the performance drops logarithmically in a striking similar pattern. Additionally, we introduce an ablation where instead of hiding VQA examples, we hide MNIST digits throughout the sequence. So we can hide a number in here, and now the prompt is simply list all the numbers you see in the image sequence. The way that we extend this ablation is by not only hiding one number in the haystacks of a given size, but also hiding up to 8 digits, or up to, n-1 digits in a haystack of any size. From this extension of the needle in a haystack test, we're actually able to create extended forms of the needle in a haystack retrieval accuracy graph, where here, instead of just having a binary test of retrieved or not retrieved at each position, we can actually have an accuracy rate over all the different digits from 1 to 10, or from 0 to 9, which are accurately hidden in each position. And we can see some striking trends. For example, the drop-offs and biases in preferred positions in different sequences depends between the models. For example, Mantis tends to prefer needles that are hidden at the end of the sequence, whereas GPT-4V has a very slight bias toward needles hidden at the beginning of the sequence instead. And you'll note that these plots look very different from the simple retrieval accuracy of basic needles in text form on video frames that were demonstrated in prior work. So this is sort of an attempt to answer this question of how do we know if an evaluation matters? Because we have this continuum of task difficulty and ecological validity where we start with this simple needle in a haystack test. This is the thing that we already know how to evaluate, and we know that the model succeeds on it. Then we have the real world task that we really care about testing, the contextual extractive reasoning task. And by introducing this intermediate task of single frame extractive reasoning over non-coherent videos, we show that this is a task that should be a little easier than the contextual extractive reasoning. And it certainly is more easier for us to collect these samples. And there's this chain of necessity between them, where obviously, in order for a model to do single frame extractive reasoning, it doesn't have to be blind to certain frames in the sequence. So obviously, if a model fails at single frame extractive reasoning, if a model fails at needle in a haystack, single frame extractive reasoning will probably also fail, because that's a more complicated task along this spectrum. And by demonstrating that the model fails at this task, we can also argue that the model will probably fail at this more sophisticated and expensive to evaluate task, even though we don't actually have the data to evaluate it. So this idea of lower bounding for ecological validity can be applied to a lot of other domains. So through this work, we showed that the implicit claim that's being made with needle in a haystack tests actually does not hold, and that the demonstration of simple visual needle in a haystack retrieval does not demonstrate that the models are capable of extractive reasoning. Needle in a haystack tests are easy to make, but they're not applicable to the real world. And this result helped inform the public, where it got covered in TechCrunch article alongside some work with Mohit Iyer's group at UMD. And yeah, it's a good example of helping inform the public through our research. Okay, so now I'm going to pivot to discussing the second project based on our NeurIPS 2024 Spotlight paper, who evaluates the evaluations, objectively scoring text-image prompt coherence metrics with T2I score. So what is a prompt coherence metric? Well, they're broadly useful in multimodal AI research because they allow us to produce some sort of automated judge that, when given an input prompt and the generated image for it, can assess how well the semantics of the generated image conform to the requirements that are implicitly present in the prompt. There are two prevailing approaches to performing prompt coherence evaluation. The first kind are known as embedding correlation metrics. One example of an embedding correlation metrics is clip score, which simply takes the input prompt and the input image and embeds both of them using clip, and then takes the cosine similarity between the two in the multimodal clip space to provide a score. The other popular kind of metric are VLM question answering based metrics. An example of a VLM question answering metric is TIFA, which takes in the input prompt first and uses an LM to generate a set of implicit requirements which are present in the prompt. Then these requirements are fed into a VLM, which looks at the image and answers each of the questions about the implicit requirements in order to produce an overall score, which is the requirement satisfaction success rate. So, how do we know whether the VLM question answering metrics or the embedding correlation metrics are actually better? Well, the conventional wisdom is that these VLM question answering metrics are better, not just because they provide an interpretable score, but also because they were found to better correlate with human judgments. But here's how those human judgments were actually assessed. Two unrelated images that may contain some errors because they were generated by a text image model are presented to the metrics alongside their generating prompts. So here on the left, we have a picture of a blue house with a tree, where the house is not blue. And on the right, we have a picture of a black cat reading a book, but the cat isn't reading the book, it's looking away. What we do with these is we get a panel of human annotators to provide Likert scores of how well they think the generated images match the prompts. Then we have the existing text-to-image faithfulness metrics assign their scores also to each pair of image and prompt separately. Then whichever text-image faithfulness metric comports with the relative ranking that's provided by the human annotators over that pair is considered the better metric. Is this method valid? In our NeurIPS 2024 Spotlight work, T2I score, we set out to meta-evaluate these text-to-image faithfulness metrics and answer this question. So let's test TIFA on some images that we can generate ourselves. Here, once again, we have the prompt, a black cat with green eyes reading a book, and we can generate some images of it using Stable Diffusion. Now, let's collect the scores that TIFA provides for these. There are some issues with these scores. First off, these two images are both perfect. The cat is there, the cat has green eyes, there's a book, and the cat is looking at the book, clearly reading it. And yet, one of them gets a perfect score while the other one does not. Furthermore, these two images in the middle also present a failure of the metric. In one of them, the cat is looking away, and in the other one, the cat is looking towards the book. And yet, they both get assigned the same score. The key insight here is that we can't rely on subjective human preference between unrelated images as a basis for determining which metric is better. After all, if we have one judge that prefers the black cat image and another judge that prefers the blue house image, one annotator might think that the blue house error is more severe and thus prefer judge 1, while another annotator might think that actually the cat looking away from the book is the more severe error, and thus the metric that prefers the blue house image is actually the correct one. This is a fundamental disagreement with no basis for resolution. However, if we instead do a pairwise comparison between two related images that exist relative to the same prompt, we can then describe clear counterfactual differences between the pair of images that serve as a way to arrive at annotator agreement. And through this counterfactual-based consensus, we can make a more confident argument that one metric is better than the other. To perform this evaluation, we gather semantic error graphs, or SEGs. Semantic error graphs are a way to organize many images relative to their input prompt. So here, if we ask for a lady wearing red playing tennis on a green court, we can generate a bunch of images and manually determine that they're all perfect. Then we can identify requirements in the prompt, similarly to how those VLM VQA metrics work, and determine counterfactual differences that could exist between the images relative to the prompt. This allows us to extend out a directed acyclic graph, which fully describes a hierarchy of different images containing different errors relative to the prompt, relative to each other. In this case, we produce this graph by manually writing prompts which ablate those characteristics out of the input prompt and allow us to fill in this tree. We design the tree first and then generate the images. However, these manually designed error graphs are of questionable ecological validity. So, we also produce wild semantic error graphs, which contain in the wild natural text-to-image model errors, which just simply occur similarly to our black cat examples naturally. So we can ask Stable Diffusion, for example, for a picture of a brown elephant in a red car. And we know that one of the things that text-image models really struggle with is proper compositionality. We can then generate a bunch of images relative to this prompt, and our hypothesis is that because these are more ecologically valid and these images are much more closely related, and because these errors are generated through the fundamental incapabilities that vision language encoders have, that these examples are going to be harder to classify than those wildly variant, manually designed semantic error graphs from the previous slide. In order to convert these sets of images into a semantic error graph, we first organize them into nodes just based on how they are different relative to each other, and then that causes the hierarchy to naturally arise. And after describing them, we're able to also determine that these sorts of walks through this graph exist. So taken together, these produce the T2I score meta-evaluation suite. We have this collection of these different semantic error graphs slotted in. We have around 200 of them that are collected first. Then we introduce sets of meta-metrics that allow us to check how well some metric correctly orders them. So like, let's say that we have these scores over this set of images. We can then look at each descending walk of the nodes in the error graph and then check, for one thing, how well does the model correctly order the scores along those. And then also we can check other properties. And this is the other half of our evaluation set, these semantic error graph specific meta-metrics. So the first meta-metric that we have is to capture ordering, which is a extension of Spearman correlation over these error graphs, where we just take the scores assigned by some pair of models over each of the nodes in this graph. So note that at each node error count there are multiple images, and then we can just look at Spearman's rank order correlation in order to get a score over a single walk of the graph, And then we can average those over all the walks in a graph to get the graph level ordering score. And then finally average over all of the semantic error graphs in the data set to get an overall score for the performance of a model with respect to ordering. Similarly, we can check how well these scores assigned by the models separate the populations of the nodes by using the Kolmogorov-Smirnov statistic. The two-sample Kolmogorov statistic is simply the maximum vertical height between the CDFs of the scores in the two populations. In this case, the populations being the scores assigned to all the images at node 2 and the scores assigned to all the images at node 1b. So here we have the results for those, first for those embedding correlation metrics across the entire T2I score benchmark. And we see that, okay, they're getting around 70% in the Spearman correlation rank ordering score. And okay, the VLM metrics do slightly better. And then we also have this other class of metrics that it's not important to get into that do quite a bit worse here. Okay, and then I click again, and okay, yeah. So there's a slight gain in performance over those using the VLM question answering metrics that were widely believed to be better. But when we move to only the semantic error graphs containing natural real-world errors from text-image models, we find that the performance gap closes considerably. And for the separation score, the difference is even more dramatic, where there's a clear overperformance of the embedding correlation-based metrics over the VLM metrics. Now, the real problem here is that, okay, maybe you'll say the VLM metrics are still outperforming them though, so why should I care? Well, the reason why you should care is because it's extremely expensive to use these correlation metrics in terms of flops per image over using these simpler metrics. So here is the graph of the conventional wisdom. The evaluation of these different metrics using unrelated pairwise preference correlations, like the example I showed before. And based on this sort of evaluation, there's really a dramatic difference between clip score and TIFA using different embedding model or different VQA models. However, when we switch to our evaluation and check those same models, the increase in performance almost completely disappears. And we actually see that some of the variants of TIFA that were beating clip score on the original evaluation now are actually worse than it. So through this project, what have we learned? Well, the status quo before this project was that based on unrepresentative meta-evaluations, which don't really isolate the core characteristic we care about in text-image faithfulness, there was a flawed conventional wisdom that gave practitioners the wrong idea about the relative hierarchy of how good different text-image faithfulness metrics are. However, once we introduced an objective meta-evaluation technique, which captures the core thing that we really care about in faithfulness evaluation, we gave a better picture of the reality of the relative performance of these metrics, and the illusion of superiority of the VLM VQA metrics went away. This idea of constrained specificity is another insight that can be applied more broadly to evaluation. Because the unrelated pairs were both subjective and carry other unspecified preference information mixed in with the isolated understanding of just the relative error counts, isolating them gives a better picture of how well suited a faithfulness metric is to the task that they're actually employed in. So I will conclude this presentation with takeaways. We had two questions that we set out to answer in this presentation. How do we measure what matters? And how can we know if an evaluation matters? And we introduced two projects that demonstrate a way to answer those questions in some real-world task. For the first project, the answer that we arrived at for how do we measure what matters is that focusing on ecological validity to a real-world use case is the goal, And the way that we can do this is by finding a lowest complexity task that a model is incapable of performing. In this case, it was extractive reasoning over unrelated images, which lower bounded the real complex task that we really cared about, which was extractive reasoning over complex and natural sequences. For the second question, the example project that we presented to answer the question of how do we know if an evaluation matters was this faithfulness evaluation meta-evaluation project that I just showed. The way that we were able to know if an evaluation, in this case, a faithfulness metric matters, was based on whether it precisely models the underlying logic that drives the judgments of humans that it's seeking to replace. And by thoughtfully designing a meta-evaluation that isolates this logic and doesn't mix in any other unrelated preferences, for example, we were able to isolate and capture this characteristic alone. So thank you for your time. That's it for this presentation. And I hope that you'll check out the full texts of these papers, which I will provide in the comments. Thanks again.